All righty, we're good to go. Can we go? Yes. Okay. Hi, everybody. It's my great pleasure to introduce today's speaker, Alan Dressler, who I assume most of you know, many of you very well. Alan is a long-time Carnegie scientist. I'd say one of our most prominent scientists in the history of the institution, to be fair.
Thanks.
There you go. Yeah. Joined here in 1976 as a Carnegie Fellow and then joined the staff. And he retired, I was trying to remember, maybe about 10 years ago.
2016.
Yeah, something like that, but has continued to be extremely active, as you'll hear today, which is super exciting. And Alan has worked on many, many fundamental problems. He's probably best known, I think, for the clusters of galaxy work, galaxy evolution in general, but also black holes in galaxies. I was checking yesterday, he has over 50,000 citations, over 800 papers. Probably the most famous is the morphology density relation paper, which is one of the most cited papers of the last 40 years. But also lots of things. He was part of the NIRCam team. He was one of the first people to show black holes existed, supermassive black holes existed in normal galaxies. What am I forgetting? He was responsible for IMAX, the most used spectrograph at Magellan still.
Yeah.
Still the most used. I think I was actually the first science user on IMAX in 2003.
Right.
So it's October of 2003. So it's been 20 years. And then many other accomplishments. So I have to mention at least some of these. So one is he is a member of the National Academy of Sciences, not surprising based on all that. He was the Newton-Lacey Pierce Award early in his career from the AAS. That's one of the ones given to early career work. He got the Public Service Medal from NASA in 1999. But I think the real, perhaps is what will end up being one of your more important contributions that we're going to hear about today, which was he chaired the committee JWST and beyond back in 1993 to 95-ish. And that was the committee that actually led to James Webb Space Telescope. So, and now today we get to hear all the exciting things that he's done. You've already published a couple papers on James Webb in the last year.
Yeah.
Just so we're going to hear about that today.
Second one.
All right, let's welcome Alan to the stage.
Thank you, John. Very nice.
I don't know if that's,
I think I've got one.
you got one.
Is the mic on? You guys can hear?
Good. All right.
Thank you very much, John. And speaking of that, I wanted to start because this project is very much related to what happened back in 95 that John just mentioned, that I chaired this committee. And I wrote this little thing, so when I don't spend more than a minute on this. But I think it's important to me because it really relates very directly to what we use to sell this telescope. 30 years ago, ARA sponsored a study of what might follow the Hubble Space Telescope, especially important if its planned repair, that was 93, was unsuccessful. Soon after, HST was restored with spectacular results and unprecedented public enthusiasm. HST's early work on distant galaxies inspired the JWST and Beyond Committee to recommend to NASA an Origins program, recognizing this once in a civilization opportunity to look back to the birth of the first stars and galaxies. In this key cosmic event, the production of the first heavy chemical elements in galaxy reservoirs to hold them and build them up. The universe took a sharp right turn from heat death oblivion to a future of fantastic complexity to planets and life. Our origins lay in that epoch. So we knew at this point in the middle 90s that HST was going to take us very close. That was the excitement, that it took us to higher redshift galaxies than we really had anticipated. People tried to estimate and were way too conservative about what would happen because actually distant galaxies were brighter and smaller. So we worried about this 1 + e⁴ dimming. Both those things were sort of overcome. And so we saw galaxies going back to within 2 billion years. But then, of course, the view faded because it's a hot telescope, warm telescope. And you move into the near infrared, the telescope is glowing and you can't see anything. So that was, in fact, I wanted to say that just when you look at these pictures, this is a talk on star formation histories. When you look at something like this, you could see, I mean, just visual clues that there is a lot of variety or diversity in star formation histories. The trouble is, you can do this But how do you connect the dots? How do you know what changed in the what and what physics was going on in that process? That's the problem. So we said, if you could build a near-infrared space telescope, you could take that to its completion. You could see galaxies actually forming for the first time, like I said in that sort of previous slide. And I still consider this sort of the prime mission of JWST. And it's not just the literal work I'm going to talk about, because I'm actually measuring star formation histories in a very direct way. But now there are, hundreds of people, thousands, I guess, who are working on the first galaxies. It's fulfilling its promise of sort of breaking open that subject. Star formation histories have been a real trouble spot for astronomy. Been very frustrating since Walter Baade at this observatory discovered two populations of stars, old and young, in M31. Baade was successful with this because he used photographic plates that he could resolve the stars. The challenge is when you have a situation like this one and you put it all down a slit, you have many populations all mixed together. Still, it would seem like you could overcome that relatively easily because every generation of stars is a unique spectral energy distribution that shows its age and how it changes as the population ages. And here is, in such a plot, the energy distribution going from O and B stars up here and down through the A stars to older stars like the Sun. And you see that these templates for what the energy distribution looks like change very markedly through this region. But you also see that when you get to 1 gigayear, the light is no longer coming from the main sequence stars, but in fact, from stars going up the giant branch, and that's highly degenerate. So the templates, it's a word now I can't find, they all begin to look alike, and you cannot use this technique of simply decomposing the SED into populations. But there is a way forward in this, and Dan is here, and he started a project that really led the way to what I'm going to talk about today, of analyzing the SED for the part that you could recover something about the star formation history, that part with things younger than 1 billion years where you could resolve what was going on. This was part of he did a survey called the Carnegie Spitzer IMAX survey, Dan, which took galaxies redshift 1.5 to sort of 0.3. His goal was to watch the creation of passive galaxies over that very long time. And he chose to use a Spitzer selected sample because it would be much less affected in terms of mass limit than the surveys that were being done with sort of bluer selections of galaxies. And then he did a very big survey, 3 fields, I think, that were 5 square degrees, to get enough galaxies and enough volume that he could look for environmental effects of what makes galaxies go from active to passive, from star forming to passive. And this all has to do with a prism that was made by Steve Scheckman, which was revolutionary because it didn't disperse the light in such an inconvenient way, but the dispersion became sort of uniform. And with that, we got lots and lots of spectra, I should say, Dan did. Go on. So just to, take a SED that looks very familiar, the data you see here from one of Dan's spectra are these blue lines and also these bands of photometry that were done at various places. And what he's done here is fit this brown line, which is an old stellar population, older than a couple billion years. And you can see it's a very good fit. This is an old galaxy. It happens to be a redshift of 0.65, but you could easily deduce for this that all the light is coming from old population. And that's very typical. Okay, but it didn't tell us much about star formation history. This is sort of why. The one thing that we had accomplished in star formation histories was the production of this diagram, which was that Hubble was taking pictures all around the sky. And little by little, there was enough of a library developed that you could measure for any volume of space at a different distance, the ultraviolet flux that was coming from those galaxies, and turn that into a star formation rate. So this sort of emerged, I'm not exactly sure I remember anymore, but it must have been 1990, 2005, maybe? Does anybody remember? Anyway, this was a very famous diagram, and it showed we knew something about the evolution of the entire set of galaxies in the universe, or representative set, all through time. You're all familiar with this now, and it rises, and then at cosmic noon, as they call it, it peaks, and now we're in this really sharply declining area. So if this picture is representative of all galaxies, not just the average galaxy, then we expect that star formation today, galaxies should be shutting down. I wanted to say that, a lot of people stopped working on the problem when this came out. They said, well, we know it does this and it comes down. But Simon White told me in particular, I said, what about the individual histories? Well, I said, Dressler, you're worried about weather. I'm interested in climate. And that was the end of that conversation. He really thought, for a physicist, this is all they needed to make their simulations. Why go any further? Well, so sure enough, when we look back today, and we could only do it 2 billion years that we could tell what's going on, and then it's just old, we see that the rate of star formation is declining in almost all galaxies. So all we've learned is we can't get the history from here, so why not try going further back and then applying the same technique? And that's basically what we did. Gus Ulmer had been working, we had a group was studying clusters with IMAX, and Gus was interested in the field population. We sort of did these clusters and put the field all together in the idea, we didn't eliminate them by photo Zs or anything like that. We wanted to know what the field was doing in which these clusters were immersed. And Gus found something very interesting. He found that at about a redshift of 1/2, there were many galaxies that had star formation rates that were high and should have had a lot more mass. You could measure the mass and you could measure the star formation rate from the blue light, basically. And if you looked at those two things, it implied it had not been forming stars at that rate or even higher in the past, as expected for most galaxies. In fact, they were light. He called them young galaxies. We were very resistant to that. But the point was, we didn't target those specific galaxies. That was a sort of a statistical result. But with Dan's study of the CSI, we could try to measure star formation histories in this regime around here, look back 2 billion years from the galaxies we were using, 0.4, 0.5, 0.6, and that would take us, within shooting distance of cosmic noon, and we'd have more of a history. And we could see whether, in fact, there were galaxies with rising star formation rates. That was sort of the question. And in fact, we found such a thing, a really rather large component that at that redshift, that intermediate redshift, about 20–25% of the galaxies at that period showed most of their mass coming from after redshift 1, which does not really line up with this Medal diagram that we were just talking about that shows everything sort of in decline if everything is following the average. Well, this seems to argue against that. And it says that you could see that here's one that has half of its population is old. There's a template down here that describes that. And then these other templates are for younger populations. I should probably have told you exactly what this was, but this is the star formation rate, and this is the buildup of the mass. And so this is one in which it looks like half the star is formed by redshift 1, and then the next half to where we observe it. But there were lots and lots of galaxies we could detect nothing before the 2 billion years earlier, sort of redshift 1. And we got very worried about that. And Dan did a fantastic analysis. We made, synthetic galaxies and put them through the system. And we eventually concluded, even though we were quite worried, that we'd have to publish it. And I say it was very troubling because even today you think about this, if you believe in halos forming first and, stars forming with the gas that's in the halos, you can easily imagine processes that might have delayed the star formation, some dynamic processes that were to do with the gas, but you can't really stop the halos from forming. So you have this question, why would you have 20% population here that had managed to survive to redshift 1 with all their gas, or most of it, half of it? And that's very puzzling. I have to say that this didn't end in a happy way, because we published a catalog, we published images, we sort of begged people to go out and make measurements, use your own programs for doing the population synthesis, and show us what we did wrong, because it's a very sort of troubling result. And the long story is short. Nobody did that. I found that the people who were doing simulations felt that they couldn't really go into the simulations and pull out individual histories. That's not true anymore, but at the time, that's what I was told. And nobody, as far as I know, actually went out to make new observations. But what came out of this was my realization, somewhat at the time, that because I had joined the NIRCam team and I was thinking again about this first galaxy thing, that this problem that you could only see back 1 or 2 billion years in a history was just going to be so much easier at the dawn of time, because all the stars were within 1 billion years. So if you could get the light, I didn't know how hard that was going to be. If you get the light and get the SED, you should be able to decompose it into these things. And that's basically what I've done. And A stars are the sort of dominant light that's coming from this period. Goes into the Bs a little bit, but they happen to be very, suitable templates in the sense that they're main sequence stars. There's no post-main sequence evolution involved. They have hydrogen opacity. There's no metal lines that really dominate. So that's not another factor too. They look to be a very good standard candle that happens to have ages in the sort of billion mega year range. So this is what some templates look like. So at the time I was getting into this, Brett Robertson in the NIRCam team and some other people, very good people, were trying to prepare for the avalanche of data that was supposed to come from the imaging programs, the deep fields. So he was producing, they were trying to produce a synthesized sky of what it might look at redshift 6 and beyond. And he did that using Bruce-Wall models, Bruce-Wall-Charlot models, BCO3, and generating SEDs in the bands that NIRCam was going to sample. In fact, he did all the filters in NIRCam, which is a big task, but probably not more difficult. So he predicted what the fluxes would be. And there was another effort to sort of make images based on what we knew and make an artificial sky. So we had artificial sky with artificial fluxes. It was called the data challenge. And we all operated on things like that to see what kind of answers we would get. Now, unfortunately for me, they didn't bother to make star formation histories as part of that. They just sort of picked galaxies that were, let's say, passive or things that were forming stars, but really didn't think very much. Well, I don't know. I don't know why they didn't think that was interesting, but they didn't. So these templates that he produced have the fluxes from the stars and also nebular emission from the whatever lines are in the H2 region and non-thermal continuum when that's there. So this is kind of what they look like. And this is now starting at redshift 12. So I should also say that Dan Stark then went in and prepared for me, because this is what we needed to look at that period, a set of templates that began at redshift 12, and then we did integer epochs, redshifts, to 11 to 10. This is what the spectra would look like. If it started at 12, what would it look like? Like that, very, very blue. At 11, it's like that, flatter, 10. So all these templates looked very different, and that makes sense because they're A stars, and as you saw when I showed you that plot of the templates, there's a lot of movement between the 100 million years and a gigayear. So this is good. It means that the templates are not all piled up on top of each other, which is the normal problem, but there's great sort of non-conformality that allows you to do this. And then so there's this one set of them, and then there's a set of templates that starts at redshift 11, and then you evolve that. What did it look like at 10, 9, 8, 7, 6? And then there's a set of templates that are contiguous star formation, constant star formation at the epoch of observation. The only time you see star formation in this process is at the epoch of observation because it disappears so fast. These are long epochs, so you can't see anything for the previous epochs about its star formation. Those guys have all evolved away. So we're getting there. So I wrote this program called SED star that was really based on what Dan had done to fit fluxes in these 7 bands primarily. There's one down here, it's 0. With these templates that would represent the mass in A stars at all these different epochs. And I'll show you how the program works, but this is a plot here of a solution that the program found by forming stars at these epochs, and this is the mass that it produces. And when you do that, this is very noisy data from the original glass survey that was done by Tommaso Tre and collaborators. And so they were great, but there were 24 objects that we could do. There were a lot of problems reducing really deep JWST data at that point. So I was lucky to get anything out of it. But in fact, the program seemed to give things that were sort of as expected. And that really surprised me a lot. This thing is the range of solutions if you perturb the points by their error bars. This one is not particularly well constrained. Nevertheless, you can see the shape is recovered. And of course, over here is the chi-square of the fits as it goes through this process. So you could watch it go through this process. This is now from the new survey, for the bigger survey from NIRCam, Team JADES, a galaxy that has rising flux to the red. And the star formation history that it solves for is one of declining star formation over time. And at this point in the program, I decided to color code the different population templates and contributions so you could see sort of how it adds up. So those are the things you have to make that shape. If you start at redshift 12, the program does, and you say only stars at redshift 12, can I match to the SED? Well, it's horrible. If you say I'll start at 12, but I'll observe at 11, you get a little bit of star formation here, but that's really fairly minor. But even looking at it at 11, it's a better fit than the first one was, somewhat. But as you add subsequent templates together, you see that there's always a star formation at the beginning, but it's getting to be a better and better fit. Until finally, you have this good fit, and then the next one. Whoops. I guess that is the last one in this. That's very funny. I thought there was one more. Must be the other thing. I've got the, that's right. It's in the other batch. Okay, so that is a good fit. And it's based on, as I said, there's only sort of 28 of these templates that go from 12 to 11. And there's only 28 of those. And there's these 6 constant or continuous star formation templates. And what that, I should have sort of mentioned this. So you're adding templates and you have all the fluxes are related to each other. That's fixed for every template. So there's no chance to fit individual points like that. You have to add up what you've got and hope that it can match something like that. So if, for example, the stars at redshift 1, or let's say redshift 6, were very different than stars today. Maybe it's not A stars anymore or something. it would just fail to do this because it's kind of like a chord. You have these 7 frequencies and the ratios are always fixed, but the volume can be changed by taking the whole thing up and down. It's a vector problem. Anyway, that's how it works. And as was found in the first paper, but now in this second paper with much better data with a 900 galaxy sample, there are 4 basic types of galaxies with star formation histories recovered. The first one here is, I mentioned all this about their great work at producing the photometry and the catalogs. The first one in the upper left is one template only describes that star formation. Unlike the one I just showed you that took like 5 templates, it only takes 1. It tells you that it takes about 3 × 10⁸ solar masses to do that. And time scale is sort of 100 million years in that bin. So it says there are stars that are less than 100 million years old, which when added together will, give you this template, and it's a good fit. Next to that is 2 templates in which it's what I said is true. One template is this redshift 6, but there's another one. Old stars are seen. Redshift is at 12, and that's really very massive, 5 × 10⁸. 5 times 10⁸, excuse me, solar masses, but considerably more than the last one, which also has some continuous star formation. I like this because you can see how clearly these 2 templates actually make up the SED. And then you get the sense if you threw anything else in there, it would not work. It's very clean. Then there's a lot of these things that sort of have 3 epochs of contiguous star formation. A lot I could say about this, but not worth really going into. But this is only 3 epochs, but at this end of the scale, that's almost 500 million years. So it's actually a pretty good stretch of time. And then this one, which you saw something like that, where 4 epochs are used. And I have to say, don't overreact. There's a gap here, there's a gap there. The program where we're trying to get the idea, is it a long star formation history? Is it a short, bursty star formation history? And there's reasons why you can expect this, not just because of the noise in the measurements, but it's a non-negative least squares program that does the fitting. And so it's not allowed to make negative star formation, which it would like to do. Make it just so it does what it has to do to make the best fit it can. Please.
So I see you're noting nebular emission lines here, and I'm curious what you are doing with those in these fits.
Okay, so the first thing to know is that the fluxes that are predicted include a standard emission lines, but we can bet that H alpha is sometimes more than 0.3. So the basic thing has been corrected for, and then you sort of see them shifting up or down. So the whole thing in the appendix, a long sort of analysis showing that they don't contribute very much to the flux. And basically the only thing that would happen is those bigger bands. I left out to say where is this one? These 2, this helps because you have 2 medium bands. And when you see an elevated like that, it's pointing out that there is emission in this one, and it looks more because of bandpass is smaller. And if you see something like this, you probably have sampled the continuum. So you could ask how much emission is in there. And so, right, exactly. So that was very handy to have those. So anyway, there's a nice section on it. I think, people brought that to my attention. They were very worried about it. I threw this in sort of out of place because it sort of shows you where we're going with this. So now those 4 different types, a single burst, stochastic, contiguous, and long star formation history on the corner, they just color coded. And the points I wanted to make, so this is redshifted This is the log of the stellar mass that is finally produced. It's the end point in the process. And these colored points seem to cover sort of the whole range, and they seem to cover the whole mass range. That's just an interesting comment. It is like there's a gross shift in star formation type from bursts here to dot bursts there and things like that. And here's a scale just for so you go with this from 300 million years to 1 billion years. That's the time period being covered. And these are the epochs in terms of the length of star formation. So when I say there's a burst here, somewhere within this 100 million years, a lot of stars were formed. There are A stars that have ages of that or less. I can't tell what happened inside that bin, but I know the stellar mass is there. And when I say it's a burst, I'm saying that I don't see any stars from this one or this one or this one or this one. So I'm not bringing this up because it's like 100 million solar masses in 100 million years is only 1 solar mass per year. That doesn't sound like a burst, but actually I don't know anything about what happened in that interval in that epoch. It's just that a whole lot of stars were produced and in that period of time, and nothing from nothing. There wasn't anything before it. Of course, there's a limit here. It's only sensitive to about 50, 30 billion solar masses. And that's just a signal to noise effect. There's a signal noise of 5 cutoff in the SEDs. But there's no upper limit here, but it looks like this sort of upper bound of kind of 10 to the 9 solar masses holds all the way through. That in itself, I think, is very interesting. It's not growing like that. And I think that also is consistent with this idea that it's mainly starbursts, like the title of my talk. Let's go on. So I made some more of these cartoons. You can now do, everybody probably knows this, but the animated GIFs where you can put each step together. And the journal is actually going to put this in there. So that'd be kind of cute. And you could see how you got lots of solutions, but it only takes one when you get the right one. Maybe I have to trigger the next one. Now, I should say, always the first ones look so terrible, but I haven't thrown any of the galaxies that are redshift 10 or 11 because that's the kind of thing they actually fit. But not these things, which are more like redshift 6 and 7 that I've chosen for the models. Anyway, you guys get the idea. So I will go on. Okay, so this new paper has a big sample of about 900 galaxies, and they're in the deep good south field. We have 7 broad bands and these 2 medium bands. It's part of the JWST program. So we've expanded the redshift range to go from 6 to 12. We have a much bigger sample. And the papers include not just those 4 examples, but 4 more panels of 18 galaxies to show you that those really are the characteristic shapes. There are, for example, here, 5 starburst galaxies shown, where one, and I've got to, I've cheated a little bit by adding a little on the before it, but in fact, it probably straddled 2 epochs in the way this works. And then there are, 4 examples of these stochastic ones where there's 1 epoch of star formation and then what I consider a real gap of a few 100 million years, and then more. And interestingly enough, it's always a declining thing. You'll see that pretty much for all these star formation histories. They're either level or declining, and I think that's significant. Then there's these sort of triple things, and then here are the longer ones, which kind of can almost be like, depending on how big the gaps are, they can be like stochastic too. So that is a full sort of sample, and like I said, this is at redshift 7. There's one for redshift 6, there's one for 8 to 10, and then something for, there's only 23 very high redshift galaxies in here. So let's see what's next. That won't work actually. you give this talk, I mean, there was a nice dramatic thing here. I was supposed to forget that this actually came up, and then it just sort of slowly appears. Give this talk, everybody says, oh, what about dust? And I rock up to them, I've ordered to say, what about turbulence? And what about magnetic fields? That shuts them up. So it's a really good question. And it's sort of self-answering in this case. This is a no dust sample. Doesn't mean it's everything in the field, but it's pretty clear that there is no signature of dust in any of these. And I'm certainly not the only person that says this. It's been common for people, let me show you this, in the field who are working on them. They don't see much evidence of dust in a large fraction of the galaxies. That there are some that are a lot dusty. So here is like a AV of 0, and here's 0.4 and 1, and this is log flux here. These are pretty steep compared to anything I've shown you. So there's nothing like a few tenths of a magnitude of AV. In fact, I think it's probably limited to about a tenth of a magnitude, so it's pretty small, as it may be. But it did make me think about, let's see, where does that go? It goes to here. It did make me think about the fact that I don't see any rising star formation rates. And they must have been dusty at some point as they formed the stars. So my sort of putting this together is that there was a period of about 10, 20 mega years in which all these stars formed in a very dusty environment. And you have to look very hard to see them, like with MIRI, but the problem is MIRI doesn't have the sensitivity, I believe, to see things of this mass or flux in the environment. So we could find dusty things, and I should have said that in this sample of 900, there were about 30 galaxies that had really steep, red to blue, things like that. I don't even know what to make of them because I can't fit them to a redshift or anything. All that information about the A stars has been wiped out. It's just sort of being cut by the absorption. So I don't know. So if it has this dusty phase, then after that, as I said, maybe that's where all the star formation happens. And then there's a sort of a dribble for the rest of the time of that epoch, or maybe it shuts off altogether. It won't matter because those stars are going to be a 50 to 100 million year old population in that bit. The O and the B stars will be gone, and that's what you'll have survives. So that's my story, and I'm sticking to it, as they say. I showed you this already, so now we know we have these 4 types. There isn't anything very obvious about their fractions over time. People have wondered about this. There's a lot of blue things here. There's a lot of, I don't think that's real. It has to do with the way the program, there are interpolations between this bit and that bit, and I think it's stuff like that. At any rate, it's not the kind of thing I think you could imagine that really turns on and turns off. The blue ones are the long star formation histories. There's some of them all the way along, except not here. You see, well, maybe that's part of selection. In fact, you can't really, it's a short. Now you should have some that go back that far. There are just a few. Anyway, and as I said, you have this kind of upper limit, which is interesting that 10 to the I solar masses is what is done in this period of time for common galaxies. So this is everything that's in the field. This kind of means these are the ancestors of L-star galaxies. So it's very interesting. They have 10 to the 8th solar masses, 10 to the I solar masses, if they're fortunate, at the end of it, but they've got a long way to go. By redshift 2, they're going to weigh, 10 to the 10th, 10 to the 11th solar masses. And most of these are bursts, as I said, and there's no sign that they're even going on with star formation now, then, at that point, because it looks like they were just bursts. And if all these things were long star formation histories, then you just see a higher percentage of these things all the way along. But it says that most of these things are just popping up. And it looks like maybe that explosive event was enough to stop things for a while. But it's really interesting because it's got to get busy pretty fast, and it's got to really grow. Plenty of mysteries. Oh, and here are the fractions. Did I actually get it? 53% of them are this one epoch burst. Another 20% are, two things very well separated. And then we got only 8% of the things I sort of expected we'd see, like cow models, smooth, ongoing star formation. So that's a surprise to me, at least. This is just a rough, breakdown of that. So you see that this single burst kind of things are pretty much constant over time. And so are these. I don't think there's anything here to read, but I'll mention this later in connection with a paper that has come out claiming something different. So just for fun, I tried displaying this in a way where you'd sort of see not just one point for the mass, but where it started, the first star formation, and then connecting to when you observe it. And that's what this is. So these are the single bursts, and these are the sort of multiple bursts, mostly two. And you can see there's kind of dominated by bursts coming out, not some sort of building up of mass in individual galaxies. There's sort of one-timers in this period of time. And it's a little bit better here because you've got sort of this upward slope of they come in here and then they add mass during this period. So that's the counter example. But it's not very dramatic, I would say. Then I just put them all together because I thought it would be interesting to see what it looked like, and added them up. So you could see this sort of phenomenon that the bursts are single events and they sort of start pretty far down, but eventually they catch up to everything else in terms of the total mass. These are integrated lines here, the continuous ones, and contiguous and stochastic, which are, high. This is kind of an artifact because they have widely separated bursts, so they're going to show up here. They're fairly massive bursts that started and then it completes. But when you get done with all this, you find that except for the continuous ones, everybody else contributes about the same amount to the mass. And I had something to say about that, but I've quite forgotten. But there's solely a factor of a few.
Do you have this plot where you divide the stellar mass by the rate of stellar mass production?
No, I guess I could do that. A sort of a star formation history. So what do you want to do? Are we doing it point by, what are we doing? We're
the star formation rates rising from your collection of galaxies.
Well, I don't think so because, well, shouldn't say that. The bins are bigger here. So, yeah. Yes, I imagine they must be at some level. But I don't think it's a very...
All your galaxies, for the half that are all single bursts, they're clearly rising star formation. Right? So at least you know then that's the problem.
If they're single bursts, they're rising star formation history?
Presumably. Or all your single burst ones older bursts?
No, they're just less than 100 million years.
Right.
Stars.
So, the mass was...
You mean inside there they were? Well, that's true, but I kind of tried to average over bigger amounts of time than that, because when you see these long continuous ones, it's kind of what you expected. We'll add some mass now, we'll add some mass. And that just doesn't seem to be the big story at this particular time. But, maybe when you think about that event that made the 10 to the 9 solar masses, it may have been just so explosive that was it for a while. I don't know.
Alan, can I ask a related question?
You could try.
So when you've got that single burst and it's producing all the, statistically all the light you essentially see.
Right.
Right. Do you have a sense of what the upper limit is for how much mass would have been in the earlier bins? Are you sensitive, if a galaxy had a quarter of its mass before that burst?
That I'm sensitive to. So like I said, it's incomplete down below 10 to the 7.5. but complete enough that down there, 10 to the 7th, I think, they're just screened out for low signal to noise. So I thought about that, and it really would take a lot of things down there, and it just didn't really seem to make much sense. When it goes from here, then it goes down there and does this for a while. Well, maybe, but that is probably insignificant. I mean, it just comes out that's a few percent added.
Right. You'd love to know, right? If,
I would.
If you knew, if half the mass was present before the burst, you want to make sure you can rule that out.
Well, that I think
10%,
you can.
Easily rule out half.
Yeah.
And it sounds like.
And 10%, if it were several epochs in between, like those 2 burst things, and or something, you could get 10%, I'm sure, maybe 20. But then what? It sort of doesn't really solve your problem of why so many stars here and then nothing, right? Or little. Well, we're getting done, which is good. So one other thing you could do is you could look at the distribution across the sky with type. And I did this. And I was really excited when I saw this, because I thought I saw all kinds of, voids and things that weren't these things at higher density regions or something. And none of that bore any fruit. This sort of see what the field looks like now. And I'll show you that in the most boring sort of form. So I performed local density versus the types. It's a little hard to see the colors, but you kind of get the idea. These are the bursty ones that are light red or orange. And then the greens and the blues are the longer types. And I don't really see much separation of those things, meaning that the star formation histories do not seem to correlate with local density, at least not at this level of local density. But I do, after I did this, I remembered that even for the original morphology density relation, the effect really only held in clusters. And when you got to the edge of the cluster, to the field, you didn't see anything. I did that, Postman-Geller did that. And really, this is the field that we're talking about. So maybe that's no different. Of course, that doesn't mean you really understand it, but maybe it's no different. So if you split these by redshift intervals, I think you really begin to see large scale structure. I mean, that's real. There are voids there. Let's see, this is 6, this is 7, and this is the 8 to 10. And, Drew and I are going to look at this some more. Not much more I could say about that, except it looks like there's large scale structure. And, this is entirely covering the reionization epoch. So, you might hope that you would see something associated with opacity, to do with seeing through reionization, but probably not. And then I did find something interesting. So I made a plot. I don't think I talked about this last night. Don't have 23 galaxies above redshift 10. Sorry. But I have lots of galaxies that form their first stars at redshift 11 or 12. And I think I know that, I think I've actually detected that. So this is a map of the sky of the 200 galaxies that have their first star formation at the very top of the ladder. And something I think interesting seems to emerge, and that is that there is a high density region here that kind of goes from here to here. There are 30 galaxies in a 2 square arc minute area here. It's pretty dense. And about 40% of them are the SA4 types, the long star formation histories. No reason for that to be in particular. And that compares to 8% for the whole sample. And you can sort of see that if you look around here, it's much lower. But both here and above and below, it looks like there's actually an enhancement. So maybe there is a relationship with density in the sense of the galaxies that have longer histories are in more neighborhood kind of situations. The ones that are bursty are out by themselves more, maybe big mergers or something. But maybe the process of building is a little bit more continuous and peaceful in these higher density regions. Who knows? But at least there seems to be something in there. And as Dan has always reminded me from our study, you see a spatial correlation with something else that has nothing to do with space, you have to take it seriously. It really shouldn't be many times higher population in this particular region of the sky. So that's interesting. Okay, so I think we're sort of finished. You know, I think I've tried to demonstrate that this program works, and it's not my doing, it's just A-stars. And the lack of rising star formation histories, I think suggests to me that I'm not seeing that first phase, and that's where the dust is. And the variety is such, and really 70% of them are things that are in this bursty type of behavior. So my goal for the future are to try to get these, like we unsuccessfully did with the late bloomers study, try to get this into the community that models and tries to explain things. I'm working with Andrew. We're looking at Galacticus simulations, and also with a couple people from FIRE who are working on this very, I'll say something more about this sort of starburst kind of behavior. And Andrew sent me this a while back. I don't think it's actually, we have another plot now that I think is more revealing, but it was interesting that the first day he picked a bunch of 4 times 10 to the 10th solar mass, 6 times at redshift 4 halos, and produced this kind of star formation histories. And at least some of them seem to have the salient amount of mass and time scale. And at least here, you know, there wasn't anything going on afterwards. Although I think, so I asked him what happened, and he went into simulations and he came back and said more complicated things to me. So I don't really know if we ruled it out, but it means it's not a totally alien result in terms of Galacticus. And I think the same thing is true with FIRE, but let me go on about that. But again, I'll say again, you know, if they really are quitting somewhere after they make this first burst, how do they actually wind up being L-star galaxies? So there have been a lot of papers about bursts. This from Msun. This is one of the FIRE people. I wanted to show this just because it took a while to figure out that these really are things above redshift 10 and not the kinds of things that are in my sample. In other words, they're much rarer and brighter. So they are trying to understand this. It's real. This particular suggestion was based on the idea that maybe they were bursting, but therefore their mass to light ratios were changing because they had, and so the mass that people had estimated that should be right for these galaxies was correct, but they were much more luminous for the period of time, and they could show that they thought they populated this excess in a reasonable way. But I have to say, you know, even though I don't have the same sample, I have an analogous situation on these, and I don't measure the light, I measure the mass. I measure light, but it's always fixed to the mass of the A stars. So I couldn't, you know, escape through this little tunnel. You know, whatever we see, it's actually the mass that's been produced. So it makes me a little dubious of this, even though there's a more massive and rarer things. I don't actually see why that would turn on for those galaxies. But this is there are dozens and dozens of papers about trying to explain this. There's also a paper that uses SEDs that are in the literature and tries to fit an SED, not in the way I have with decomposing it into stars, but just its sort of general shape. They are trying to figure out where these galaxies sit on the star-forming main sequence and whether they're above or below. And they show that there is an evolution of whatever it is they measure here. I could not really go into it with time. So this is high redshift, medium redshift, lower redshift, and they see a shift in the distribution that says to them that these things are bursty, but after redshift 9, there is a sort of transition to things that they call secular, which they mean forming stars in a sort of continuous way. And so I've already showed you that by that one plot with the, I don't know if I put this in again, that I sort of showed you a rough graph of what the, that's why it was here, of what those proportions are. I don't really see anything, especially at redshift 9. There doesn't seem to be any migration over. I don't really understand very well how they did this. So I have to learn more about it. I think it's worthwhile measuring actual star formation histories rather than trying to go straight from the SED to some sort of a, I'm not a big fan of the star forming sequence anyway. Here is something I did find very interesting. Andy is here, isn't he? So Andrew, I was listening to a talk at the celebration they had over at UCLA for Malcolm. So Ranzini was on, and he was talking about multiple generation populations in globular clusters. And I have to admit, I hadn't followed this for a long time, but apparently it's really well observed, right? There are multiple populations in what, half, quarter, what? Most globular clusters? Well, this is rather embarrassing because the star formation that is to produce the first population, presents a pretty big challenge to what happens afterwards. So in this paper, I mean, he was talking about this, I had never heard of this, the idea that apparently has been around for a while of something called overcooling, but I won't go into that, but what it is that if you imagine that all stars more than 10 solar masses collapse directly into black holes and do not therefore explode with a lot of feedback, you could certainly explain, and that's what he thinks is really going on. And I don't remember if they're really, are you familiar with this, by the way?
It's from Alfio's book that I a couple of years.
Yeah. Maybe you'll tell us about some of those in the question and answer. So it's very interesting to me because I think I'm in the same boat. I think these 10 to the 8 solar masses, which are in kiloparsec size volumes, if that, they should blow themselves up. I mean, they should have blown themselves up before they got to that. That, I think, is why surprised people that you would even find things like that. So again, I'd love to appeal to that if that really has any validity, but there are opportunities for explaining why these systems were able to survive when people generally thought they wouldn't or didn't. And this is just one more thing. There are other people working on this idea of trying to prevent, this is a feedback-free starburst, another way to do it with something that Deckel has, but I think I was told this is a sort of highly contrived situation. The problem for me is I don't see a way to measure star formation histories like that, because if you have a bunch of bursts that are young like this, I don't know how you can look at a galaxy and say that that's what happened, because unlike with these A stars, which last a long time, those all kind of go away. So you can do for any one burst, you could say, what's the ratio between the ultraviolet flux, which has one time scale, and the H alpha, another, and you can sort of say whether it's a kind of a bursty thing or not. But whether those bursts have been repetitive, I don't know how you do that, except statistically. You could sort of go into the samples we have and measure the burst frequency from spectra, for example, and try to put together a self-consistent picture that allows you to say whether this is the kind of thing that's going on, which I think I told you I don't really believe. I think it's more of a, well, maybe he means in the time when it was all formed, when it was dusty. So I guess that is where I will quit and take your questions. Thank you very much. It was all totally clear.
A lot of questions, right?
Other questions online?
Oh, sorry.
Hi. All of the ones that in my catalog, about 85% of them are verified by the easy redshift thing. I don't really, the SEDs are a good way to measure redshift. I mean, if you're just going to use some sort of photo Z, you're actually stepping back a level. But to be perfectly honest, it is mostly the Lyman alpha break that really sets these things. And I did, when we were flashing the sort of recreations, the 2 points at the beginning had a big effect about whether it was a good solution. A lot of times it looks great, but there's flux coming out here and you know you haven't got the right redshift. So I don't think they're all correct, but I think that probably 80–90% of them are about right. I wouldn't spend all the money to do spectroscopic redshifts of all of these. I think, unless you could do something else with the data, which you probably could.
Hi.
Sorry, go.
Yeah, okay, so I noticed that there's just a span of maybe a few degrees in your sample set from this time.
It's not even that. It's 25 square arc, but it's
It's
a small
okay.
region
Oh,
of this
really
stuff.
small.
Yeah.
Okay, so 6 months later, the James Webb telescope's on the other side, looking the other way, and it's going to end up seeing 10 to 12 redshift galaxies.
Sure.
So has anybody really thought about the geometry of what's really going on? That it's not that those galaxies are fleeing from us, but the direction that light's coming is from when the universe was smaller. And
Well, we believe that that is an effect of 4-dimensional or higher geometry, that it's easy to imagine we are stuck if you think of 3 dimensions. And how could it be that we look out and we see a space that was smaller? But if you go down and make the analogy to a 2-dimensional world where you're the flatland creatures and the universe is just a sphere, you find the same problem, all these sort of geometrical paradoxes. And so that's how we explain that. It's when you are looking out there, you're looking to an earlier time, but it is bent around you in a space that you cannot perceive.
nicely said. Okay, thank you.
Okay. I saw one in the back.
I have a question about reionization. I guess I just recently learned that like the latest estimates for when reionization, and that was kind of have been pushed lower to kind of redshift 5.5 or 5. So which would place all of these galaxies in your sample kind of before reionization.
Yeah.
So does that change like you're thinking about like what the population kind of what is going on there?
Is that based on the CMB?
No, I think the Planck was more like 7, but then it was like actual measurements, like galaxies of.
Well, that's interesting because I, heard at that JWST first year conference, Hatim Atak presented a study that was showing what the flux was from low mass galaxies that have long thought to be the ones you needed to do the reionization, and confirming that in fact there were enough. More than enough to do that, but only he was working at redshift 8 or 9 or 10. So I don't know. So you're saying this is a measurement that is measuring the reionization state, but not talking about how it got there?
Yeah, I think that was the claim.
Yeah, this is from quasars, right? It's just the very tail end, not like 50% or something. That's just more extended, I thought. But Michael,
and the neutral stretch is going all the way down to redshift 5, but
Right.
the volume is already mostly ionized by redshift 6.
I think
Okay,
it's
but
hard to
that will
argue.
still like be at a lower redshift than these galaxies. These are all higher than 6.
Redshift 5, that's right.
Yeah.
Fair enough. I mean, it's hard to argue that these are galaxies that actually are between 6 and 12.
Right.
You've got the Lyman alpha break and everything. But that's certainly relevant to what output they are making and whether that has anything to do with the reionization. Yeah, that's for sure.
Do we
I
have
see one more. Andrew, were you going to say anything more about other things that have been suggested to explain how globular clusters can make more than one generation?
If you don't want to make the ion, you have to blow it out first, right?
Sorry, say again.
Then you make the different, like, you make the signatures of the different populations below the ion production.
like this. So intermediate mass HED stars. And then you convert, and then you can, the signatures of these multiple populations are decline in oxygen and an increase in sodium. And so to make that with intermediate mass HED stars, they call it hot rock burning. But then, how is it that the iron doesn't very much, so you have to blow that out? But when Xeni's thing is, okay, they all collapse somehow, and it must therefore be a methodically dependent, thing where you don't get an analysis, you can everything explode. So I guess that.
I know that his paper spent a lot of time talking about the elemental abundances too, and that sort of this contradicted that, and it wasn't a simple story.
Yeah.
So
Yeah.
it's very interesting. I mean, I think about the way these modelers have tried to predict star formation from the lambda CDM simulations and things, and they've been happy about whether they got the star formation rate right, with time or things like that. They're entering if it can be done. They're entering a regime in which we know so much about star formation at this early period, including the elemental abundances, that is mysterious even to those who are not trying to model it. I can't imagine what the increase in computer power and ability to ferret out these kind of things going on in the collapse of a dark matter halo. But that's where I think the attention is going to shift. Those kind of puzzles like this.
All right. So the TAC needs to get to lunch. So we'll thank Alan one more time.
Thank you. Thanks, Tom. That's really great.
Thank you, John.
I have a couple of things I wanted to bug you about.
So the TAC is working?
Yeah, we're working.
Yeah, we took a break.
You won't have
Watch him
the
talk.
Alan Dressler to kick around, Eddie.
Yeah, I'm gonna
That
give
is
you all-
true. We do appreciate that. It's helpful not to, every proposal we don't get is good. Thank you.
Where did Dan go?
He ran to grab lunch, I think, or
Oh. Oh, he said he had questions, but
Oh,
he
he knows where to find you though.
I'm afraid so. Yeah, I think it's grown a lot in a few years, in a year.
Yeah,
That I feel much more confident about.
yeah, it's nice and it's nice to have the recording of this as well. Yeah, the save this.